All right, so good morning or good afternoon, depending on where you are, everyone. Welcome to Modeling 101, Part 1, this webinar session for 2024. Today, we will walk through the fundamentals of watershed and water quality modeling. But before we get into that, I just want to briefly introduce myself. My name is Maddie Keefer. Hello. I am a water resources engineer and modeler with Tetra Tech. I've been with Tetra Tech for about 4 years now. And over that time, as well as some time previously, I've worked on a variety of watershed and water quality modeling projects with both EPA and partners at several state agencies to tackle and investigate a variety of water quality issues or problems. I by no means consider myself to be an expert on water quality modeling. I haven't used every one that is available, but I do feel comfortable sharing the basics with you today as well as next week for part 2 of this session. So looking forward to it. Thanks for being here. And I will let John go off mute and briefly introduce himself as well.
Yeah, thanks, Maddie. Hey, y'all, I'm John Mallard. Unlike Maddie, who's been with Tetra Tech for years now, I've been with Tetra Tech for about 6 weeks. But if we're counting the sort of first time I got in the stream and took a water sample, I've been working in the kind of hydrology space for about 15 years now, both standing in streams and behind computers, driving models. Primarily working in watershed modeling, but some lake and larger river modeling peppered in there as well. And come most recently from the Forest Service, and here at Tetra Tech, I'm mostly focused on our work in water quality and watershed modeling. So I'll pick up from Maddie for the back half of this, and for now I'll pass it back to you, Maddie.
Awesome. Thanks, John. So this session is designed to give you all a solid foundation, hopefully, in modeling principles, some terminology, some modeling applications, ideally setting the stage for more advanced discussions later on. As Jesper mentioned, in particular for attendees who are planning to attend the upcoming in-person modeling workshops in Philadelphia for the 2024 year. But regardless of your experience with modeling, this session is tailored to help equip you with essential knowledge to participate more effectively in those future training workshops if you choose to join them. All right, so before getting into the bulk of this, a few quick logistics items. So hopefully everyone sees a Q&A tab near the top of your Teams window. That is active, and everyone should have access to drop questions for John and I in there. Feel free to do so. And ideally do this instead of going off of mute. John and I will have breaks throughout this session where we'll try to answer as many of your posted questions as possible during those breaks. It does appear we have a solid number of attendees joining us today. I'm seeing about 68 attendants, I believe. So thanks so much for being here. But with that in mind, please try to keep yourselves muted throughout the presentation. Depending on timing and interest, there might be some time at the end of this for verbal questions, but then we'll also rely on that Q&A tab for posted questions. All right, so lastly, to make this virtual session a bit more interactive and engaging, we have attempted to sprinkle some poll questions throughout the presentation. We're running into a few possible technical difficulties with that, just due to the fact that we are all from different organizations joining in on a joint Teams meeting. Hopefully things work for us, but if not, John and I will pivot and try to still be as interactive as possible with you all. So we will be pausing the webinar session at certain points to post questions in the chat. And then review those results as a group if technology plays nice with us. All right, so let's get into it. So the objective for today's kickoff Modeling 101 presentation is to provide you all with an overview of modeling topics and common terminology and to provide a foundation for the second part of this webinar, which will be held next week, as well as for the upcoming in-person workshops, which are scheduled for the week of September 16th. In general, the intended audience for this first presentation are managers and staff who are water quality regulators or practitioners, but who have limited experience with water quality modeling. For people who work with models quite a bit, this overview might seem a little basic, but for people with zero modeling experience or somewhere in between, this presentation should be helpful to help lay the groundwork for the what and the why of water quality modeling before you get into more detailed topics in future training sessions. So topics that I'll be covering include a watershed approach to modeling and some general modeling terminology. And then John will take over to provide an overview of model development steps and a quick crash course in some commonly used models. Next week, the part 2 session for this webinar will provide an overview of model calibration, scenario and TMDL development, and some helpful modeling utilities that can aid you in your work. So with that, I think we can go ahead and jump into a first poll question, if it'll work. Kirsten, could you please launch the first poll for folks? Okay, great. So I'm seeing that pop up in the chat. So if folks could please look at that in the chat box and attempt to respond. I, again, don't know if this will work with different organizations joining into teams, but hopefully so. Yeah, okay. I'm seeing that it is working. Okay, great, awesome. We'll give folks a little bit of time to respond to that first poll. Yeah, Audrey, sorry about that. I was seeing the same issue on my end. If you'd like, feel free to just type your answer in the chat as well. If you'd like to engage that way, we'll kind of monitor that as well. So far, it's looking like everyone knows what a model is. So we're starting strong on that. Okay, well, we have a good amount of responses so far. So in summary, folks who can see this in the chat box, you see that we're all over the place in terms of the level of experience that we have to date with modeling topics, which is great. That's what we wanted. You know, we want to help lay additional foundations for modeling with folks who are truly beginners, but then also this will be a good refresher for folks who have experience, whether intermediate or advanced experience with watershed and water quality modeling. Right. Okay, so I'll kick things off with some general points about the modeling process. So to start, let's define what a water quality model is. So the textbook definition is shown on this slide. I won't bore us with reading that aloud, but what a water quality model really is an equation or a series of equations that are developed to simulate an environmental condition. And then those equations are typically run by using either a spreadsheet or a computer program. So a model is a water quality tool that can be used to help inform decisions. These modeling tools are used for a variety of topics, but some examples include assessing exposures to pollutants, projecting future conditions, supporting permits and trading, and assessing contributions of individual sources to a cumulative source problem. So the graphics on this slide help to describe the difference between watershed models or water quantity models, which simulate land processes and water quantity interactions such as infiltration, overland flow, etc., and water quality models on the right-hand side of this slide, which include equations and complex algorithms that describe the processes affecting things like dissolved oxygen, alkalinity, nutrients, sediment, and algae. So there are some models that are a combination of watershed and water quality models, but it's important to note that some models represent either one or the other, and we often use a two-model approach in some cases to simulate both the water quantity and the water quality pieces. All right, so water quality models have great utility, and a few examples of their usefulness are listed on this slide. So some Clean Water Act programs that water quality models can be useful tools for include total maximum daily loads, waste load allocation calcs, setting numeric nutrient criteria, and the development of best management practices or BMPs to help protect water quality in rivers, lakes, and other water bodies. So I think we'll go ahead and go for poll number 2. So Kirsten, if you could launch that in the chat, that would be great. So ideally, if this works for some, it'll be a word cloud option. So this is meant to be just open-ended. In general, what types of applications for models are you interested in using models for? So Clean Water Act programs, climate change studies, just general watershed planning, just to give you a couple of ideas. We'll give folks a bit of time to respond to that and then work on sharing those results of the word cloud, see what it looks like. Yeah, thanks. Feel free to, if that poll is not working for you, just put your responses in the chat. Yeah. Just based on responses in the chat, developing TMDLs is a big one. Permitting for 319 programs is a big one as well. All right, go ahead and get your answers in if you haven't already. And Kirsten, can we see if that word cloud can now be posted so folks can look at it? I'm not sure if that's an option, but hopefully so. All right. Kirsten, no problem if we're not able to see the word cloud in general, but if so, and there's a general like response, or even if you can take a screenshot and post that as an image in the chat, that'd be great. Cool. All right, great. So here's what that word cloud looks like. Thanks everyone for being patient as we work out these technical difficulties, but hopefully everyone can see that. And also You can see it in the chat as well if you want to look at that screenshot posted by Kirsten. But in general, TMDL development, that's popular, and that makes sense. Especially, with this group being affiliated with EPA or invited by EPA, working with EPA on these Clean Water Act programs. A big part of water quality monitoring, assessment, and ideally improvement is related to total maximum daily loads. And because those are complex and require a lot of data, a lot of thought, a lot of calculations, models are really good tools for TMDL development. In general, Clean Water Act programs, nutrient modeling, watershed protection and planning, all of that applies. Great. All right, so we will move on now. Okay, so while we're talking about model utility and the question of why use models, it's also important to discuss some model limitations and uncertainties that are also certainly a factor in water quality models. So the natural environment is complex and variable, and models are always constrained by computational limitations, assumptions, and of course, knowledge gaps. So some folks in the room might be familiar with the famous adage by our friend George Box: all models are wrong, but some models are useful. So essentially what he meant by that simple statement is that though models are imperfect, they are helpful in interpreting past or current data and helping diagnose a problem. They're an important line of evidence for whatever issue is being investigated, and they provide an imperfect approximation of reality. So they're not the only answer, but they're an important line of evidence for particular water pollution and water quality investigations. So again, the natural environment is complex and variable, and models only approximate natural variability. They're simplistic representations of reality, like the comparison we see on this slide here, where on the left we have a three-dimensional stream system of variable elevations, land uses, different soil types, and then that is simplified down to the 1D or the 2D scale with a model approach that sometimes follows a process flowchart scheme similar to the two figures that are shown on the right of this slide. All right, next I will briefly cover an overview of the water quality modeling approach. So water quality modeling often follows the watershed approach for the type of problem you're investigating or the questions you're seeking to answer with your model. Sometimes a large-scale modeling framework might be necessary to simulate all the various stressors and processes that affect an in-stream water quality parameter. So some examples of all the stressor sources and processes on a watershed scale are shown in the image in this slide. So next we'll take a look at some ways that the watershed approach can be applied in modeling efforts. The watershed approach often utilizes a linking of models where different categories of models are grouped together to simulate all the different processes that are of interest. In some cases, 2 or even 3 models can be grouped together as shown in the graphic here on this slide. So let's say you're interested in what's going on within your watershed and all the terrestrial non-point source loads and the processes going on within the main water body itself. And then in some cases, like modeling an estuary or a lake, you might also be interested in modeling the physical hydrodynamic processes that are occurring, like currents and tidal influences. Well, all of those individual models, so the watershed, the hydrodynamic, and the water quality model, can be linked together to come up with some really complex models. Not all water quality problems and investigations warrant that level of detail and that level of modeling approach, but it is doable and can make for a robust, comprehensive representation of reality. Another piece of the watershed approach to water quality modeling that's useful to note is that it involves multi-year continuous simulations. So ideally, 6 to 10 years or even more for a model simulation allows for modelers to capture both wet and dry years with precipitation, and also get a more comprehensive picture of the weather and the hydrologic variations that can occur over time, as well as how the watershed and the water body of primary interest reacts to those variations over time. So here's an example of a model configuration that might be appropriate for representing water quality in a river system. So you might opt to have a watershed model that handles the simulation of watershed loading, such as upland runoff from non-point sources, atmospheric deposition, and point source discharges from upstream facilities. And some examples of watershed models that can handle those aspects include LSPC, HSPF, SWIM, and SWAT. But then you might also have a receiving water quality model that simulates the in-stream response to those watershed sources. So this model type, when linked to the watershed model, can integrate the point and non-point sources through a one-directional data exchange, and then simulate that in-stream or in-water body response. So two examples of receiving water body models that are common are WASP and Qual2K. Just to give an example, I can share on this type of linked model configuration is for the Jordan River watershed of Utah, which empties into the Great Salt Lake. Last year, the modeling team at Tetra Tech worked with the Utah Division of Water Quality to update an existing HSPF watershed model and extend it to a more recent time period. And then that was then linked to an existing WASP model for the Jordan River main stem. All right, now an example of an even more complex 3D model system might be appropriate for a water quality modeling project in some cases. And an example of a case where that might be appropriate would be for modeling a pretty large lake or estuary system. So in this 3D model system, you might have a watershed model such as LSPC, just to name one, to simulate the watershed loadings. EFDC could simulate hydrodynamics for the lake. And then you could also have a water quality model such as WASP for simulating the water quality response within the lake itself. To share another Utah example, Utah DWQ and the modeling team at Tetra Tech are actually currently working on developing numeric nutrient criteria for this region, for the region of Utah Lake, which is to the south of Great Salt Lake. It's located in Utah County. And that project is using a 3D model approach. HSPF is the watershed model, EFDC is the hydrodynamic model, and WASP is the receiving water quality model that's simulating the processes in Utah Lake itself. Okay, so it's worth noting that in these types of model configurations, dynamic models are typically required, and steady state models, which are more of just a snapshot in time, are rarely used. And don't worry too much about the difference between those. Here in just a couple slides, I'll get into more of the details for those two model categories. All right, so here's one more example of a complex linked water quality model. And we're showing it in map format for now. So in this case, you might have one overall watershed model with all the contributing drainage area for an outlet water body of interest. In this type of linked model, you could also have a number of water quality tributary models. And then you could also have a vertically layered lake hydrodynamic model, which then all gets linked to a receiving water quality model like WASP or C=W2. All right, next I'm going to cover two quick slides on some data needs for water quality modeling. This is a quick rundown of some data considerations that are necessary for building a water quality model. But during the upcoming in-person workshops for the WASP, the SWAT Plus, and the Modeling 201 track, for those who are attending, each group will certainly go over more detailed modeling data needs. All right, to start, spatial data is a big piece of the puzzle when developing a water quality model. Examples shown on this slide include hydrogeography data, such as National Hydrography Dataset flow lines and catchments, digital elevation models, and hydrology and water quality station locations for observed data that would be used to calibrate your model later on. And all of those data sources relate to and help with sub-watershed delineation. Next, weather data are very important for model development to provide the forcing functions for the watershed interactions. And lastly, land attribute spatial data are critical model components for parameterizing hydrologic runoff and other landscape processes that are happening in the upland areas. And some examples of those could be soil coverage information, National Land Cover Dataset or NLCD, impervious surfaces, as well as NLCD land cover. All right, and another data need for model development are time series data. And just a few examples, this is not an extensive list by any means, but a few examples of those required time series data are shown on this slide. So as I mentioned on the last slide, weather input data are often needed for developing water quality model. Point source data from NPDES permitted dischargers are often gathered as a pollutant source for models. And then, of course, you'll want to obtain monitoring data specific to the day collected for the extent of your model boundary area. And that's the purpose of that is to use it for calibration to see if and change parameters as necessary to have your model output that is simulated line up with reality as best as possible. So that observed data can include USGS streamflow data, water quality observations, and if warranted for the pollutant you're investigating, even phytoplankton or periphyton data as well. All right, so now that we've done a quick overview of the modeling process, the watershed approach to water quality modeling, and some basic data needs, I'll next cover some basic types of models. But first, let's take a brief break and see if there are any questions posted in the Q&A tab. I'm not seeing any.
It doesn't look like yet. Yeah, you're doing a great job, apparently, Maddie.
Be gentle if you do have questions, but feel free to ask them. But no problem if there's not any questions from folks right now. But if any come up, go ahead and post them. But good. Our beginner modelers are grasping things really well, and that's great. Okay, so as I'm transitioning to these basic types of models, just ask y'all to please remember that this is a pretty generic overview for today's presentation. We could probably spend an entire modeling webinar series to cover these types of modeling topics and all the options that exist out there. And those types of more in-depth trainings and webinars are available. There's soon to be some for some folks that are attending in Philadelphia. But for today, we're keeping it pretty simple and giving basic overviews. All right, so to start, I'll cover two general model types. These are essentially the two different generic types of water quality models. The first one is an empirical or statistical model. So those kinds of models are based on observed relationships. And the chart on the left is an example of that. It might look to you that it's not really a model at all. You might think, well, that's just a regression line with some data plotted behind it. But you can use those observed relationships, put some equations behind them, and then perhaps combine all of that with some known information about your watershed of interest and use that to create a model to represent what's going on. But on the other hand, there are mechanistic or process-based models. And those models simulate the properties and interactions that are truly going on within a stream or other type of water body. For example, there are equations that are describing how nitrogen and phosphorus or whatever your pollutant of interest might be are actually working within a stream as opposed to the empirical model, which just uses that measured data. And there are pros and cons to both statistical and mechanistic models, and the pros and cons for statistical or empirical models are shown on this slide. So just to name a few pros, data requirements are generally much smaller compared to mechanistic models. So because of that, it's a lot faster and easier to set those up and develop them. And it directly links a stressor of interest to the response. So in some cases, it could be a little bit easier to understand those statistical models. But of course, there are cons. So you are constrained by the data that's available. And because of that, there's limited ability to extrapolate outside the range of original available data. And I'd in fact, and I think any modeler would caution against extrapolating much, if at all, with a statistical model. And it may not be able to account for all response variables, whether measured or unmeasured. For mechanistic models, some pros and cons are listed on this slide. Pros is that because these models are based on fundamental kinetics and processes, you have greater ability to extrapolate to more novel conditions. These types of models might be more appropriate for looking at future conditions for watershed planning or climate change studies. And parameterization is constrained by conservation of mass and energy principles. There are a couple of downsides. They're much more data intensive, and because of that, they can be pretty time consuming and costly with both funding as well as just labor to set them up and calibrate them in order to apply them properly. And they can be misapplied if parameters within the model that you're working with are not constrained to the limits that are feasible or realistic. All right, now looking more closely at mechanistic models in particular, these can be further broken up into two overall categories, which are steady state and dynamic. So for steady state models, an example of which is the Qual2K model, mass is constant and the outputs of the model are equal to the inputs. Oh, and I do just want to note that there are examples of a Qual2K model that are steady state, which is what I'm talking about now, but there are also dynamic Qual2K model options. So I just want to put a quick disclaimer about that out there. So these steady state models follow a simple mechanistic approach where a single definable environmental condition such as flow, water temp, light, or nutrients is a focus. It is difficult to define a single critical condition for more complex water quality issues. So it's not always appropriate to use this snapshot in time steady state type of model over a more dynamic model. So with dynamic or time variable models, mass can vary. So it could, in some cases, be possible for your outputs to be less than or even greater than your model inputs due to that time varying input influence. These models can simulate responses under time varying environmental, meteorological, and loading conditions. The dynamic models are useful for situations where a modeler might want to evaluate the frequency, magnitude, and duration of response variables or chronic water quality stressors. For example, if you wanted to ensure that daily average dissolved oxygen is never less than 5 milligrams per liter, but that any simulated dissolved oxygen concentrations throughout a given amount of time never dip below that lower limit of 4 milligrams per liter, a dynamic model would most likely be the more appropriate model choice for you because it can provide that information. All right, so as we start wrapping up this overview of different basic model types, I wanted to give a quick word on the differences between deterministic and stochastic models. Deterministic models are based on a set of differential equations, like the one that's shown on the left of this slide, and they describe the physical, biological, chemical, and sediment water exchange processes in an aquatic ecosystem. The output of these types of models are fully determined by the model parameter values and the initial values that are set and provided for the model's functions. But in contrast, we have stochastic models, and they incorporate probability and randomness into the solution approach. So with the inclusion of probability distributions, random error, and uncertainty, with stochastic models, the same set of parameter values could produce different outputs from simulation to simulation. All right. So on model dimensions, models need to use spatial dimensions to make the complex world more simple. So as we can all imagine, rivers and lakes have very complex processes going on in them. And they vary in terms of their depth, length, and width. In large lakes and rivers, there's even currents, winds, and other things like that are impacting the processes going on in reality, as well as in the model that's trying to depict that reality. So one way that models simplify this is to essentially divide up a water body of interest into different parts, whether that's dividing it up lengthwise, from the headwaters to the mouth of a watershed or a water body, or to vertically stratify it when dealing with varying depths with a 1D vertical approach. You could also get more complex and do both length and width stratification. Or you could get into a three-dimensional model, which actually looks at the water body from a full three-dimensional perspective. But note, with adding dimensions adds complexity and costs related to model development. All right, so I've briefly touched on this already, but water quality models can vary in terms of what time step they're run at. And we tend to think of these in two different ways. So the first step is a steady state model, or the first type rather, is a steady state model, which is that snapshot in time type. A steady state model has constant inputs and outputs, and an example of that would be something like a mass balance model, or the more basic type of Qual2K model, versus a dynamic model, which has time varying inputs and outputs. So with dynamic models, we're not putting a stopwatch to that time period at all. We've got multiple inputs over multiple days, months, and even years. And these tend to be some of the more complex models like HSPF, EFDC, or WASP, which John is going to cover a bit more in depth in the upcoming section of this overview presentation. At this time, though, since we're on the topic of mentioning just a few commonly used water quality models, I wanted to launch poll number 3 in the chat. So we could do that. Yeah, great. So in the chat, we've got what watershed or water quality models, or both, have you used or are you planning to use in the future? To inspire you, a couple are listed on this slide, but that is not an extensive list whatsoever. So if you know of some, just want to put that in the chat or in the poll if you're able to, that would be great. We'll give you all a couple minutes to do so. And Kirsten, it might be that once enough responses roll in, we need to do another screenshot. So thank you for that. Yeah, Cormix. Yeah, in the chat, just to name some, I'm seeing SWAT. Yeah, very capable, especially for agricultural areas. Watershed model, Qual2K for water quality. Yep, bathtub, Lake 2K, Flux, Cormix, SWAT again. Oh. Feel free to take about the next 30 seconds or so to enter your answers if you haven't yet. And then Kirsten, if you could take a screenshot for me, that'd be awesome. Yeah, HECRAS. All right, I think we've given folks enough time, so if we could just get that screenshot whenever you're able, I'll share that to see what the word cloud looks like, and then we'll move on to questions. All right, hopefully everyone can see this, but I'm sharing a screenshot of the word cloud of responses, which takes all the answers and just sizes them based on the frequency of that particular keyword. Yeah, cool. So I'm seeing ModFlow, which is a super capable and popular groundwater model. Qual2K, CU Qual W2, SWAT, WASP. Yep. EFDC, yeah, Environmental Fluid Dynamics Code, HSPF. I commonly work with HSPF in my work right now, which stands for Hydrologic Simulation Program Fortran. And even some that I haven't worked with. That's great. All right. Yep, basins, that's a good one. All right, so let's move on to the model development process, which John is going to cover. So developing a model involves several phases, and it starts with model planning and tool selection, and then has several other steps related to it. Before I officially hand things off, though, I do want to just see if there's any questions either in the Q&A tab or in the chat. I don't see any on the Q&A.
Haley had a question in the chat, which Anthony, thanks, provided a nice answer to. But the question, Maddie, is when inputting data into models, are there scenarios where you're pulling out clear outliers from data sets such that your model is more accurate? I'm happy to throw an answer in there too.
Yeah. So Anthony, thank you for responding. And just for the benefit of everyone, I'll briefly summarize it. Yeah, so there are some examples when outliers would be pulled, but would, yeah, again, depend on why. There are instances where you might have a strong storm that may seem like an outlier. It's just an example, right? Where you might see a bunch of precipitation and much higher flow in whatever input time series you might be developing as an input to the model of interest that you're developing. But making sure that you're checking reality, like whether that's looking at gauged precipitation and stream flow as available to see if that actually is on record would be an important thing to do before ever removing something that might seem like an outlier. On a decade long or even longer than that simulation, you have these wet and dry years, and you of course have like strong storm events depending on the area that you're working with and investigating. And so in those cases, you would want ideally your watershed or water quality model to reflect that for the particular time. And that would be accomplished through quality input data as well as calibration. John, if you want to add anything to that, please feel free.
I don't think I have anything novel to add. I think of it kind of in two pieces, I suppose. One is a more general thing, which is that it's sort of part of the process of assessing the quality of data in general. And what Maddie said and what Anity said additionally are right on, that it's really important to sort of look closely at your outlier and determine why it's an outlier. There are cases where it can be really easy to remove outliers. I'm thinking of cases where you have sensor data, say like a reflectance value from Landsat or something like that, and you know that there's a value above which values are unrealistic or something like that. And so you can just cap data below certain values or sometimes above certain values. And then as it relates to the modeling process, I often think of it sort of as a cyclical thing where, if you're not removing things that are obviously outliers at the start, possibly during the calibration or validation period, you notice issues, you might go back to the input data and see if there are some aspects of those data which could lead to those issues. And so at that point, you might remove some outliers. Maybe a really short answer though is yes, and a slightly longer answer is there's whole long courses and philosophical discussions about whether or not to do that. And so it's sort of it's a learning process over a long period of time about removing data or leaving it in. The only other question was from Kathleen, which is about whether or not the slides are available. I'm not sure about that. I do know that a recording will be available, and if the slides are something we could share too, we'll share it through, the same channels.
Yeah. So I believe that, just since we've made some minor, recent changes to this slide deck, John, we could just provide that to perhaps Jasper or Jason or whoever, and that can get shared. There's no issue from our side with sharing these with all the attendees. So thanks for that question. We can definitely look into that for you. And just since we do have the time, Haley, yeah, good point. So you're more wondering about a scenario in which you're looking at some data, maybe it's some observed water quality data and things look wrong, or with human entry into water quality exchange and just state agencies data portals, human error is absolutely possible. A simple key error could be possible, and there are QA avenues to try to catch that and avoid it, but things can get through, understandably so. I actually recently came across that with a project I'm working on, and through making sure we did a thorough investigation on gaining confidence that that was most likely a data error with the mercury data we were looking at, observations for, we did make the choice to screen that out. It could also be a conversation of were there very outdated analysis techniques in the lab that were being used back in, say, the 80s or the 90s that don't really reflect the type of data that we'd want to be utilizing now in 2024. And so that's also possible, where you're looking at some type of pollutant, mercury as an example, where that's a pollutant that's very susceptible to changes in analytical method. And also you're looking at concentrations typically in the nanogram per liter magnitude, so that ability to catch even the smallest of differences in a small concentration matters a lot. So yeah, good point. And hopefully we helped answer that question. Okay, John, I see you're sharing now. Thanks. And I'll kick things off to you.
Yeah, so I assume we're seeing the same slide that Maddie just had up there, model selection.
Yes.
Great. Cool. So we're going to move on to the model development process. As Maddie mentioned, it involves a bunch of phases. There we go. Starting with model planning, onto the model builds, calibration, evaluating its performance, and then finally accepting it and putting it into use, putting it through its paces. For today, we're mostly going to be focusing on the planning part of this process. So that's this first piece, phase one. This includes describing the problem we're trying to solve with the model and what our endpoints needs to be, putting together a quality assurance project plan, often known as a QAP. And then mostly what we'll cover, which is the actual process of model selection. I do want to say this diagram of what all the phases is sort of implies that, you know, you do phase 1, then you do phase 2, then you do phase 3, then 4. Of course, those arrows should each have sort of an arrow looping back to previous phases. It's often a kind of iterative process where maybe you do a model build and then realize it's inappropriate, and so you go back to the planning stage or something like that. So first, a quick overview of a modeling QAP. I'll leave this QR code up there, which will take you to the repository for this EPA guidance on QAPs for modeling. If you don't have a device handy for dealing with QR codes, search terms along the lines of EPA modeling QAP will also get you there. So these are blueprints for the whole project that ensure the data and models you're using are well matched to the project objectives and goals. If you have experience assembling QAPs for other projects, they're quite similar, just tailored specifically to modeling projects. Importantly, they're required for all EPA projects. And they include a couple pieces, including project management, data acquisition, whether it's measured or otherwise, assessment and oversight for the project, and finally, standards and methods for output validation and usability. In short, a quality assurance project plan, QAP, is a blueprint for the modeling project. So it ensures that the data and the models will meet the project's overall objectives and goals. Okay, so on the model selection. So there's a number of reasons that model selection is a really crucial part of the modeling process that we think of along with building the model and calibrating it and using it. First, your project has specific needs. Everyone's project has specific needs. We're all dealing with very complex problems, many of which don't have kind of readily available off-the-shelf solutions. And even when they do, determining what that solution is itself can be very complex. Also, it's a big shelf. No single model is a good fit for every problem. There's a whole bunch of tools available to solve these problems. Additionally, misapplication of models can lead to suboptimal, or I would add even downright bad decisions. And so to this end, it's really important to understand the basic concepts and processes behind models, because this can help us decide which tool to select. I like this kind of corny stock photo of a hammer and a screw and then a wrench and a nail. You know, screws rotate, and that's the problem we need to solve. So we need a tool that can apply rotation. So the project formulation is the initial step of the model selection process. And some of the initial questions we might want to ask are things like, what do we need out of our model? For example, to make a decision or provide to a stakeholder. What endpoints or parameters need to be output by the model? What processes are inherent to your system and affect parameters of concern? Uncertainty, how much uncertainty is acceptable? What spatial and temporal scales are appropriate? And then finally, what resources are available? And the resources can be a lot of things. It could be person hours, it could be money, it could be computing resources, it could be available training, those sort of things. And some of these questions are sort of science or science and engineering questions. Some of them, of course, are really more policy and management questions. And so there needs to be a nice two-way conversation between the scientists and the managers. So running through each of those sort of questions more specifically, first, what endpoints do we need from our model? And some of the things we need to think about in terms of endpoints are, can our model simulate it? This is an early, really effective question at winnowing down the list of potential models we might use, simply asking if the model can simulate the parameters of concern. Next, what are the system pieces that affect the parameter? Thinking about processes or stressors, for example, if we're interested in nitrate concentrations in a complex reservoir fed by mixed agricultural watersheds, you might need to link models that can simulate both the watershed processes and the internal reservoir processes. And then finally, if an endpoint is based on a water quality standard, can the model simulate whatever frequency or magnitude or duration is of relevance to that standard? So for example, you might need to never exceed, or more commonly only exceed 5% of the time, some value, some standard. Or you might need a daily mean between 5 milligrams per liter and 4 milligrams per liter. Or you might need to be specifically aware of dye yield changes or fluctuations, the range over a day. Second, and this is fairly intuitive, is what's the water body type? Some models are optimized for different types of water bodies. There could be rivers, lakes, estuaries, there are a lot of others. And then additionally, what's the critical condition that you're concerned with? And along those lines, can the model capture that condition? So, if it needs to capture a 7Q10 value, if it needs to capture seasonal dynamics or provide results under a specific tidal condition, these sort of things are good ways of distinguishing models. Kirsten, if you could go ahead and launch poll number 4. So we're curious here, and we put an other on there, no word cloud. Just curious the types of water bodies that we're dealing with. And of course, if your organization like mine is blocking response, throw it in the chat if you want to speak up. So it seems like rivers and streams are clear favorites at the start here, followed closely by lakes and reservoirs. I guess that about covers the major cases. Also some folks working in wetlands and estuaries. I'm assuming a lot of y'all, including Tamara, who just responded, are selecting some sort of all of the above, lakes, reservoirs, rivers, and streams. Some folks working in urban and coastal systems as well. Yeah, so that's great. So a lot of variety there. I think one of the really important things to understand in terms of model capabilities are not only the types of water bodies that they can model, because often you can kind of, square peg, round hole, fit a system into a number of different models, but kind of the step after that, which is what are they best for? What are they optimized for? We'll talk about some of those conditions later when we're talking about specific models. Okay, so moving on. Third, what's the pollutant that you're concerned about, and what's the source of it? So Kirsten, if you could throw up poll number 5. I think this is a word cloud. So we're gonna, again, need your quick screenshotting once we've got a couple of dozen responses, and you could share it with us in the chat, hopefully. So while we're entering some of those, thinking about the nature and source of pollutants. So if we're thinking about the nature of the pollutant, we're thinking about its form. Is it pulsed? Does it come, with primarily with storm events, maybe some urban pollutants, those sort of things, or is it a chronic pollutant? characteristic of a base flow period in a stream. Are the totals sufficient, or do we need to partition it between its various chemical speciation? Phosphorus is a good example there. Do we need to, fully break it out into dissolved, particulate, organic forms? In terms of its source, primary differentiation between point sources and non-point sources. And then within each of those categories, is it time variable or a constant load? With point sources, do we have a permit limit? With non-point sources, are we concerned about its connection with precipitation as a function of rainfall? Is there ongoing modification of it through a stream channel in the form of groundwater and surface water interaction, atmospheric deposition, these sort of things? So we've got a number of responses. Kirsten, if you could share a screen grab, that'd be great. In the chat, I'm seeing nutrients, sediments, temperature, bacteria, nutrients, pathogens, DO, SC, turbidity, pH, some physical stuff. Okay. So if we could open that screenshot, nutrients is the clear winner, followed by sediment probably, and then a whole variety: chlorophyll, bacteria, algal toxins, PFAS, E. coli, DO, salts, et cetera, et cetera. So big variety there. All right. So finally, thinking about model selection, we want to think about data requirements. So things like what data are already available that we can use to calibrate or validate the model. Are those data sufficient to that task? And if not, what's needed as supplemental data? This picture here, this is Mobile Bay in Alabama. I like this. So if we're looking at it just in terms of where in the bay do we have water quality data sampled, it seems like we have a lot of data. But if we dive into it a little bit deeper, these are the stations that have more than one sample. And we actually find that potentially, at least, depending on our application, we may be a lot more data limited than we thought initially. And of course, there are a myriad of other considerations. For example, maybe having to do with the scale of your problem, temporal or spatial, maybe practical considerations. Super important, of course, maybe budget or existing experience in your team. You might have needs around transparency, like requiring open source tools. There might be, these are really important, of course, there might be regulatory or legal implications that factor into your decisions, using models that are EPA approved, or you might need to be able to defend your decisions in court. You're based on your model output. And then finally, probably most importantly, are the risks of making the wrong decisions. Are there major risks to human or aquatic life? Those sort of things. And I want to make sure that this is sort of explicit. It's really important to be engaging stakeholders throughout the modeling process. I think that's sort of generally understood broadly, but the important piece is that our model really has very little utility without buy-in across all stakeholder groups throughout the process. And that can take a couple different forms. I have two examples here. One might be a modeling work group, where you're actually talking about specific modeling questions with groups of stakeholders and practitioners. Of course, this requires representatives who have a lot of technical proficiency, so you're able to have meaningful back and forth discussions, or at least be able to provide meaningful feedback. And then additionally, it could take the form of regular engagement or informing of decision makers. And then finally, a few thoughts about model complexity. So we talk about model complexity a bunch. It can mean a couple of different things, but before thinking about what it could mean specifically, and of course, I want to qualify this with it's, of course, easier said than done, but we always want to choose a model that is only as complex as necessary to address the problem or objective. In other words, we don't want to go for the Cadillac, it can do everything model in every case. We want to sort of optimize between the complexity of the model and all of the costs associated with it, time, money, computational power, expertise, all these sort of things. So when we're talking about model complexity, it could be a reference to a few different things. A couple examples, one could be the water body type. And we could be talking about systems ranging from a simple pond or a small stream that you can wade across to complex reservoirs with lots of side bays or stratified estuaries, opening into complex bays with tidal inlets and these sort of things. Or we could be talking about the water quality processes we're interested in. We could have simple cases like tracking conservative tracers, salinity, or something like that through a system, or really complex cases where we're trying to model an entire food web. We have a variety of phytoplankton, macrophytes, these sort of things. So next, I'll spend a few slides walking through an example of the actual model selection process. In this case, we on our team were tasked with modeling nutrients and the basic food web in Utah Lake. This is an example that Maddie referred to earlier in the webinar. So with, again, the caveat that we have stakeholder engagement throughout this process. In general, it follows these steps. You're identifying the objectives, screening models initially, determining appropriate selection criteria for the final decision, ranking the models based on those criteria, and then finally making your selection. So starting with identifying objectives, we identified the need to model some broad classes of phytoplankton as well as relevant nutrients. And in this P-limited scenario, these included the various components of the total phosphorus loads of the lake. Next, we assembled a list of models with some of the basic characteristics of those models to screen out a short list of options. So we wanted to make sure that it could, model the nutrients and the food web buckets that we were particularly interested in, as well as some other concerns that we'd identified in conjunction with the client, dimensions, timescales, these sort of things. Then we determined the criteria we'd use to select the model. Those included making sure that we had the appropriate level of complexity to address the model objectives. The time scale was fine enough, the spatial resolution was good enough, the processes were adequately represented, that the model represents the needed parameters and processes, that there were readily available data or reasonable data collection to go along with the project, that we could use a tool in the public domain with high quality user manual, training materials, and that had a good user base, user forums, that they were flexible, they had open source code or modifiable modular code. And then finally, that they were broadly compatible. We were able to interface with other models and other analytical software pretty easily. So we used those criteria to rank each model that we had sort of winnowed into a short list from 1 to 4. And this is kind of where expert opinion on our team came in, because we're sort of putting a quantitative score to a somewhat qualitative answer, but that isn't entirely always the case, I suppose. And then we made our recommendations based on the best aggregate score. In this case, it ended up being EFDC WASP, a pretty complex implementation. It's important to note here, though, that one of the advantages of taking this approach, providing a recommendation like this in the form of a table, is that it allows alternatives to be readily provided. If, for example, a more, say, cost-effective or less time-intensive option than something like EFDC WASP in this case is needed. So we kind of have information about a number of alternatives ranked instead of just a single model. So moving on to close out this first part of our webinar, I'm going to give an overview of some common water quality models. We'll spend most of these last couple of slides on receiving water models, on water quality models, but I'll mention some important watershed models after those as well. So one of the things we talk about frequently in the modeling world is our stable of, quote, workhorse models. And it's probably intuitive what we mean by that. It's a model that we can and do use in a large variety of settings. But some of the specifics of these include versatility. If we can predict multiple parameters with it, if it's applicable to diverse types of problems, but particularly if it's modular, we can add and remove parameters as we need them or not. And intuitive to use, high quality GUI or good documentation, these sort of things. And then additionally, we try to favor things that are open source or non-proprietary, avoids having to deal with service contracts. It also tends to mean that it's more widely used and well documented, and often has a good track record of defensible results. And then finally, related to that as well is, we prefer something with a large user community. These are complex pieces of software often, and it's really easy to find bugs and trouble that needs shooting. And it's useful when you have a big community who either you can go to with questions or often has already found those sort of problems. A couple examples of some of the workhorses that we're commonly working with include Qual2K, WASP, SWAT, SWIM, and HSPF, LSPC. A lot of those, I think maybe all of those came up in our earlier "what models are you using" polls. So let's start with water body / water quality models. If we remember from earlier in the presentation, Maddie did a nice job of explaining the differences between steady state and dynamic models, where simpler steady state models describe a system with inputs equaling outputs, essentially giving us a snapshot of specific conditions of interest. So one nice example of that is Qual2K. And as I run through all these models, I've got, I don't remember, 8 or 9 slides. I'll just hit on a couple of highlights. There won't be anything on a test. This is just to sort of give you an overview of the variety that we're looking at, how big the shelf is, so to speak. So Qual2K, it's a one-dimensional river or stream steady state model. It's a really nice, simple model, with simple being a positive rather than a negative qualifier. It has an Excel interface. It assumes, because it's one-dimensional, that the stream channel is uniformly mixed vertically and laterally. So you're sort of modeling along longitudinally in a stream. Those stream reaches can be chained together, though, so it's suitable for branched rivers and streams and some other systems. And it simulates a wide variety of nutrients, physical conditions, biological conditions, et cetera, et cetera. Then we have dynamic models where we can simulate changing inputs and outputs at the expense, of course, of greater model complexity. One example is WASP. It's come up a few times already. This is a 1, 2, or 3-dimensional water quality model. It can be configured any of those ways. It's suitable for a wide variety of systems: lakes, weirs, river streams, estuaries, and reservoirs. Can simulate stratification because of the multiple dimensions. And it, like a lot of the models I'll throw up here, it has a modular framework that allows things to be turned on and off. SQL W2 is one we use a lot. This is a 2D longitudinal and vertical hydrodynamic and water quality model. So it assumes laterally that we're well mixed, and it can model changes moving longitudinally down, say, a reservoir or a wide river, and then can also handle vertical stratification as a result. It can be chained together, so you can have side bays coming into a system. You don't have to sort of assume lateral averaging all the way out into side bays if you're working in a complex reservoir. Branching rivers, estuaries, lakes, and reservoirs, because it assumes the lateral homogeneity, it's best for long and narrow water bodies. Also modular. SQL ICM, unlike SQL W2, it does not simulate hydrodynamics. It is a multi-dimensional water quality model, though, and it's used in a wide variety of systems from lakes all the way to estuaries and coastal waters. EPD Riv1, this is a 1D modular model that includes a component both for hydrodynamics and water quality. Because it's 1D, it's really effective for dendritic or branching river systems. EFTC is a 1, 2, or 3-dimensional hydrodynamic model. This uses what's called an orthogonal curvilinear grid. There's sort of a little Wikipedia stock image of what we're talking about there. In other words, the grids that we break the system into, the individual grid cells, aren't necessarily the same size. This can be a big advantage if we're working in, say, a coastal system where maybe we have really complex tidal inlets where we want a really fine spatial solution, but then they empty into large sounds or bays where a much coarser resolution is appropriate. So it can save us on computational time by simulating those systems in varying degrees of spatial resolution. Because of that, it's commonly used in estuaries and other coastal environments. And then finally, Aquatox. I think at least one person mentioned this as a model they use. A 1- or 2-dimensional food web simulation model suitable for a wide variety of water bodies, streams, rivers, lakes, reservoirs, estuaries. And it predicts food web flows. So it allows you to model bioaccumulation, energy flows between different sort of pots of the food web. Okay, so that's a lot. I was just sort of droning on at you. We're not expecting any of the specifics of the past couple of slides or the table to sink in. Mostly it's just useful to get some exposure to some of the model names. So down the road, you know, oh yeah, we've heard of WASP, that sort of thing. And we also just want to make the point with this table here, not any of the specifics of where there are green dots and where there aren't, but that there's lots of tools out there with lots of overlapping or differentiating characteristics. And so thinking about our water quality models systematically like this is a really effective way to select models appropriate to our project. And just quickly, I'll do an overview of some common watershed models as well. So 3 examples of common watershed models are SWAT, HSPF, LSPC, and SWIM. And combined between these 3, cover a pretty broad set of potential watershed modeling needs. In the case of SWAT, it's really effective for agricultural landscapes. So thinking about BMPs or management practices in those kind of landscapes. Has pretty limited representation for urban landscapes. HSPF, LSPC, suitable for landscapes with mixed land use, so agricultural, urban, forested, et cetera, et cetera. So if you have a diverse watershed and you need to model kind of the different characteristics of each of those, that's an effective watershed model. And then finally, SWIM, stormwater management model. This is really suitable for urban landscapes where you have really complex flow paths, piping and pumping, networks of storage, ponds and features, things like that. But similar to SWAT, but in reverse, pretty limited representation for non-urban landscapes. And similar to with the water quality models, you could see there's a lot more than just these three. And we can go through a similar systematic process, differentiating these models based on their capabilities and needs. So finally, I just want to mention a few other models and resources, just kind of throw them out there as, things to keep in mind, some names that you've heard. Two modeling tools that are really useful are, one is Hawks, which is a web-based implementation of SWOT, primarily for water quality purposes, and Cormix, which I know at least one person mentioned, which is a nice combined model decision support tool for point sources. If you're kind of just starting out, a good starting point for these sort of projects is the EPA Center for Exposure Assessment Modeling, SEAM. Really easy access to a whole range of models and modeling utilities. The QR code will take you there, or CEAM EPA will also take you there. Also, a lot of really useful PDF resources on the current status of common surface water models and their components, the underlying science. These are just two examples of them that are somewhat recent, 2018 and 2019, getting less recent, providing things like model overviews, model statuses, current versioning, these sort of things, information on data needs, points of contact or references, and a lot of lit examples of model application. And then finally, if after this you're just hungering for more and more webinars, the EPA's surface water quality modeling training website is really effective. There's a number of webinars on there. It's captured set of videos from a whole modeling series done by the EPA's water modeling work group. And I've watched a number of them at various times in my career and found it to be very effective. So just a reminder for part 2, which is next week, Tuesday on September 10th. We're going to do a quick recap of what we talked about today. And then we'll go through model calibration. We'll talk about some scenario and TMDL development, and finally some helpful modeling utilities. So thanks everyone for your attention.
Hopefully folks can join us for part 2, and yeah, looking forward to seeing you all there, and then again in Philadelphia in a couple of weeks. So that's really all we have. Thanks.